Thank you.
Hi everyone, welcome to the Space Science webinar series. Today's speaker is Dr. Oleg Korablev. He's a professor and deputy director of the Space Research Institute IKI at the Russian Academy of Sciences in Moscow. He's also the head of planetary physics. He has made several important contributions to the field. He's the PI of the ACS instrument on board ExoMars TGO, the trace gas orbiter, and yeah, he'll tell us a lot about it. Today's talk will be focused mainly on the detection of HCl and the non-detection of methane. As you know, Curiosity saw methane on the surface and variability, and there was a lot of excitement, but TGO doesn't see it, and there is controversy about it. So he'll expand more on it. So thank you so much, Professor Korablev, and it's all yours.
Thank you, Dimitri, and I'm very grateful for this opportunity to present our research. And well, yes, I will review a bit the methane and ExoMars and some other results which demonstrate that our instrument could not detect methane, but is able to detect other stuff. Well, ExoMars is a big international mission, which at some moment has become a joint mission of European Space Agency at Roscosmos. It's a Russian space corporation. It's no longer agency. And it consists of two missions, two launches. One is trace gas orbiter with demonstrator, which was not successful, but the orbiter is in place around Mars, in orbit around Mars, launched in 2016. It has taken a little time to form the orbit, and in spring 2018, the orbiter has started science operation. And the main goal of the orbiter is to study climate and atmospheric gases, but also to study the distribution of water and other things. The next, second part of the mission is now delayed to 2022, initially intended for 2018, and it consists of the rover with a particular feature of drilling and quite deep drilling down to 2 meters under the surface, and a surface platform equipped with multiple instruments for long-term monitoring. So I will just concentrate on TGO, Trace Gas Orbiter, and the general idea which is behind this mission is that the presence of life should modify the atmosphere of a planet. On the example of the Earth, we know that oxygen, which appeared about 2.5 billion years ago, and during long geological long geological lifetime times remains nearly constant, and it's all belongs. Its presence belongs to life. Also, life on Earth results in both oxidizing and reduced components like O2 and CH4 are present in the atmosphere simultaneously. And Earth, well, is a different planet, is an ocean planet, but Mars is an arid planet with remains of the atmosphere, but still we can conceive that from the knowledge of the composition of the atmosphere, we can conclude about the presence of life. It's a citation of Hitchcock and Lovelock as early as 1967. The main method TGO is using to measure trace gases is solar occultation. And our instrument is employing that method as well. Solar occultation from a spacecraft allows to, when a spacecraft goes around the orbit, observes, and the instrument is pointed to the sun, and while the line of sight is penetrating the atmosphere, the absorptions due to atmospheric gases appearing in the solar spectrum. The brightness of the solar disk is 1,000,000 times greater than that of the surface of Mars if we just observe like astronomers do. And the air mass on this oblique tangent path is up to 50 times, but at certain altitude it's about 10 times greater than from observing like in astronomy. And this combination allows to reduce the detection threshold and improve the sensitivity by a significant factor. In our practice, in our history, we have built several instruments which were employing this method as well as others methods. But these instruments mentioned here were all dedicated, some channels were dedicated to solar occultation. Among the TGO instruments, our ACS instrument is one of 4. There are 2 European and 2 Russian instruments on board. And ACS and NOMAD are quite similar. They allow to observe the atmosphere in different configurations, and they cover overall a big, quite a wide spectral domain from ultraviolet to thermal infrared. Maybe I should move this to thermal infrared. And the results related to trace gases are mostly obtained with one of ACS channels. ACS consists of 3 channels. I will not concentrate on that. This particular channel is a Shelley cross dispersion instrument. The method is quite known in astronomy. All the stellar spectrometers in the visible work about a similar way. But here it is quite a compact, it's about half a meter size of this box. And we can see here a large Shelley grating, cryogenic detector, and other elements. And on the 2D detector, we obtain this kind of stripes. Each stripe correspond to different diffraction orders, and during one occultation sequence, we obtain this kind of spectral measurements, transmitting measurements. I am coming to the main issue: is there methane on Mars? I will outline briefly the history of detection and curiosity measurements. We should note that methane variability remains unexplained because of its very long photochemical lifetime, which many laboratory and other studies try to reduce, but without much success at this moment. And I will review the TGO measurements by our instrument. First paper, then paper by NOMAD, and the most recent results published by Frankman, Messan et al. There are a number of related papers. It's only our papers which somehow relate to the subject. Historical background. The idea has a long history, as I mentioned, in the 60s and earlier. All spacecraft launched by USSR or NASA carried some instrument to detect the CH stretch, which is located at the 3.5 micrometers domain, spectral domain. And there was some curious false detections published in Science in 1966, for instance. And here you see the Janine and Pierre Cohn and Louis Kaplan are mentioning that the Martian atmosphere may have an indication to life. And Mariner 7 flyby, it was published in New York Times only, but both detections and some others, it was a confusion between surface or atmospheric features. These two in particular are here methane was confused with CO2 ice features on the ground, on the surface. Then a number of gradually improving upper limit were established from the ground and by Mariner 9 in particular. And by the way, Mariner 9 upper limit has survived quite long. And this has ended in detection, announcement of a detection by three different research groups in 2004, maybe end of 2003, and some conferences. For Mizano, the PI of PFS on Mars Express, Krasnopolsky from ground-based measurements, Mike Muma from other group of ground-based observations, but their results were published only in 2009. And this continued in 2000 by PFS observations. Even TESS, very low resolution spectrometer was used to confirm methane, but these measurements were retracted later. The whole different story has begun with arrival of SAM TLS instrument. It's a tunable laser spectrometer, a part of sample analysis on Mars instrument on Curiosity or MSL. And the rover has arrived on Mars in 2011. And the group by Chris Webster started published papers in Science in 2013. First, they did not detect methane, but then they did some positive detections, and they corrected their values, their measurements earlier to positives. In 2018, they reported more spikes, more large detections, and seasonally variable background. It's the TLS does not do many measurements during the year, so the seasonally means the data were collected over several Martian years, and later significance were criticized, statistical significance of this variability, but still there were these measurements are the most convincing to the moment, detections of methane. What remains from the methane detections is the measurements by Krasnopolsky, though criticized by some people, measurements by Formizana and Jurana on PFS, and TLS. The most intriguing part of the story is that methane variability is still not explained, given its long lifetime and fast atmospheric mixing. This graph shows some detection starting from not so long ago, not early upper limits, but there are some detections by Krasnopolsky and others, and ground base, seashell, and in the rounded square there are measurements by some curiosity, non-detections, detections, and seasonally this cloud of stars is seasonally variable background. Well, I have put here the famous plume, the strong release of methane detected by Mumma and colleagues, Mike Mumma and colleagues, published in 2009 in Science. Well, just a cartoon, quite one of recent cartoons showing the hypothesized sources of methane. It's supposed to come from underground in any case, but could be originated by some scarce microorganisms, but also from non-abiotic biobiotic processes. Could be a kind of fossil methane, but well, whatever stored in clitoris. But even if it is stored in clitoris, it should come from some source initially. And it could be released through outgassing, direct outgassing, or volcanic outgassing. Returning to our measurements, well, I remind you our initial data. That's a sequence of spectra measured during occultation, one occultation, and here, here at 3.3 microns is a range where methane could be detected. Well, the spectra look quite flat at this scale, but we do look at much increased, we zoom in to the spectra and we try to see the small variations. It's one ECS mirror TGO spectrum measured, published in Nature 2019. One of the first analysis. The data is not yet perfectly cleaned, but already in this spectrum, we see the upper limit of as low as 50 ppTV. We see places where methane lines, well, it's actually groups of lines, features could be present, but we don't see them in measured spectrum. But in turn, we see the very faint lines of H2O, which are readily measured. And zooming in, we see the measured spectrum, the CH4 and some faint absorption, but it has never been confirmed in other features of methane. The upper limit said here, it's with a huge margin. I would say it's about 50 ppTV part per trillion by volume. At that time, we have published this figure, our upper limits and nomad upper limits against the seasonally variable background methane by TLS. So we are some one order of magnitude below their measurement. New measurements published this year, well, it's not the full data set, but much more abundant data set already analyzed. Still no methane and even lower upper limits. We see some variation, seasonal, it's season, solar longitude, Mars season. And we see some variation in upper limits, but this variation actually only reflects the amount of dust in the atmosphere of Mars, because there is a dusty season and quite aphelion season, and one more dusty season, and this reflects in the upper limits, lowest upper limits we have. Another cut of the data set is the latitude, altitude, latitude profile. And here we see that actually the low latitude region, the equatorial region, is there are few measurements of methane, and the upper limits are higher. It's because the high altitudes are always cleaner, and presence of dust and clouds, even in aphelion, when the dust is low, the clouds are high in equatorial region, and the presence of these aerosols impedes measurements at low latitudes. So returning to the historical graph, we can put our measurements, cloud of ACS measurements, and well, it's well below all other detections. Here also the TLS dataset is amended a little. Of course, TGO team and our team puts a lot of attention in measuring close to Gale, to where MSL sits and measures methane. It's not, the occurrences are not very frequent, and also, as I said, it's an equatorial region, and upper limits are not that low, but still we can measure quite low upper limits in PPTV, in parts per trillion. There was recently an effort led by John Morse and colleagues to reconcile two data sets, and even considering the long lifetime and fast mixing, their hypothesis is that at night the planetary boundary level at Gale becomes much lower, and there is a kind of confinement in Gale, and all previous measurements by TLS were performed at night, where this paper by Morse and colleagues expect to have to observe this accumulation of methane. And indeed, it's a very recent result published, well, accepted for publication in Astronomy and Astrophysics Journal, that in this study, the TLS team published 3 new recent measurements of these purple measurements, four recent measurements of by TLS in Martian year 35. Two of them were done during the daytime, and all others were done at nighttime. And actually, the daytime measurements are zero. As you can see, they're positives, but the error bar crosses zero. So it confirms the hypothesis of planetary boundary layer confinement. So is our result negative? Well, we consider it is not, because first of all the recent cited papers use TGO upper limits to constrain the fraction, the global amount of methane, and to constrain, for instance, the fraction of Mars surface emitting methane. And as well, we have several positive detections. I will not read this all, but just a few examples. In the spectral range of methane, in the place of methane, we see where there is no methane, we see new CO2 lines, never detected or measured before on the ground, in the laboratory, wherever. It's the CO2 atmosphere of Mars is a kind of natural laboratory to detect such faint triply. I'm not sure how much time forbidden lines, magnetodipole band of CO2, and this detection has triggered already a number of spectroscopic studies related to that. And we found well, a much more complex structure of which was not was present in the first published spectrum I have showed you, shown, and but it was not identified, but it coincides nicely with ozone absorption, which is kind of irregular, but fitted very nicely in from our data. It was also published, and we are able to retrieve low-level, low altitude ozone in the Martian atmosphere. And well, in reply to one remark that ozone is really in place of ozone, the MSL team published this paper. So the methane is not confused by ozone. Indeed, you can see there is ozone in place of one feature they measure, but there is no ozone in the place of feature. There is no other feature where also ozone is also present. So we detect HCl for the first time. A new component is the Martian atmosphere. Hydrogen chloride, well, could be kind of expected, because it's the first chlorine measurements to be. This is the prediction, theoretical prediction, which we put in cartoon, which we put in a kind of proposal paper. But it was never detected before, and the upper limits was quite low. And it appears that HCl is seasonally variable and correlates with the dust, appearance of dust in the atmosphere. Yes, but what is interesting that when observing the second Martian year, we see also that there is hydrogen chloride appearing in the atmosphere during dusty season of Martian year 35, even though the amount of dust in the atmosphere was much lower. compared to the dust storm of Martian year 34. But what is curious, we do see in aphelion, we do see two and even more, not on this graph, even more detection, robust detection of HCl, not a single measurements, but profiles. And this puts our hypothesis that HCl is originates from dust lifted and or irradiated by UV in the atmosphere. Maybe there is a surface release indeed, and the variability correlated with dust is maybe could be explained by reduction, by destruction rather than by formation. Concluding, some TLS continues detecting background methane in Gale locally, and we do continue to improve our upper limits, globally mixed. And these two measurements are still difficult to reconcile given the lifetime of methane, which is still remain of 300 years, which still remains uncontested. No mechanism is proposed for rapid destruction of ozone, of methane, and during at maximum at 3 months, the parcel of methane, if released, should be diluted and in the atmosphere and reach all the places, the most stagnant places like poles, where we measure the best, obtain the best measurements. So there should be accumulation of methane, and we have like estimates that in 20 or even less years, we are the accumulation of methane from Gale only would reach methane would reach levels we should detect from the orbit. So the case of methane remains open. And we have a number of other results which are out of scope, but all come from ACS instrument on TGO, just for reference. And I would like to thank our team and our sponsoring organizations for being able to present these nice results to you. Thank you for your attention.
All right, thanks so much, Oleg. Very interesting results, and we are now open for questions. So you can raise your hand or type it in the chat box or Q&A box.
Maybe I'll ask something.
Yeah, go ahead.
Can you comment on the claims of methane plumes that was claimed quite some time ago? There has never been another instance when it has been observed. Is that right?
Well, plumes, it's, I came to this graph, fortunately, by chance. All these measurements, high values, are like plumes, and the most prominent is this one, seashell, which was published. Maybe I will put this graph.
They are transient plumes, are they? I mean, they just appear and then they disappear.
Right. This one. So it remains unexplained.
Yeah.
Okay. And what is interesting? For instance, well, there is no much discussion on that. If we go to this TLS results, right? There is a number of high values, this cloud and this result, one recent result published by Morse, no, not by Webster, by Morse et al. 2019. And one of these plumes was confirmed spikes. Well, it's not because they measure only instantly at some moment, and they don't measure afterwards. So it spikes one measurements. We don't know what is before, what is after. But one of these measurements was confirmed by PFS in the paper by Jurana, Marco Jurana et al. In Nature Geoscience. These values are much higher than sensitive enrichment measurements of background. And it's not very clear for me that how it appears that there were first much of that high values, and then now only one. And there are a few more points here, which I showed in some graphs. To explain it like in the frame of any model is very difficult. So what now people is trying to do is to reconcile these low values with our non-detections. But the spikes complicate the picture even more.
Yeah, this picture you showed in one of the previous ones shows a structure to this plume. It's like two pairs of opposing vortices or something like that. I mean, okay, this one here. It's very interesting, but I've never seen anything like that discussed. Yeah.
Well, it might be somebody has discussed it, but well, the main for me the main problem is that to have that you need and there was some quite adjacent non-detection to have these two points here is needs some destruction mechanism. And this has to be solved somehow. Well, if there is methane, there should be some destruction of methane, and that's really challenging to find that mechanism. If we have that any kind of destruction, we are fine. We can go further for to go to explain fine details and things, but so far we are at at large we are not okay, because we don't have destruction mechanism.
Thank you.
Yeah, there's a question by Klaus. Go ahead.
You pointed out microbes as a potential source of methane. So I wonder whether there are any rough estimates how deep these microbes may be below the surface, and is this consistent with a 2 meters drilling depth that the ExoMars surface mission will have?
Well, the depths of habitable depths, hypothesized habitability depths is like 1.5 meters or and below, because one meter is supposed to be penetratable by cosmic rays and other stuff, and so ExoMars drill is designed with account to that. Returning to microbes, the the paper by Krasnopolsky of 2004, they have an estimate of amount of life of methanogens which is needed to explain that their detection at this point, and it's actually very scarce, very in terms of sterility or Earth type sterility. It's very sterile still, and you don't need much to produce methane if it is not destroyed, because their estimate at that time was, of course, all supposing the lifetime of 300 or more of years or more.
Thank you.
Do we have any other questions? Please raise your hand.
So I guess the conclusion is that we don't know whether there is methane or not. Is that how I should think about it?
Well, I am not in position to criticize other people's measurement, and but there is a kind of a schism in the community. There are people who are convinced that methane is there, and there is quite a number that who are convinced that methane is a fiction. There is no some measurements from the ground are not really reliable, and TLS could be compromised by some problems on board. But well, it's really difficult to comment. Well, I'm quite confident in our non-detections, but we measure above, well above the surface. Our lowest sound altitude is best case is 3 kilometers, and it's on poles, not on equator, not on gale. Near gale, we can get to 15 kilometers at most, the best case. So it's not the same place. And if there is a mechanism to destroy methane, there is no contradiction.
Okay. What kinds of mechanisms might you be thinking about?
Well, there were full many mechanisms. The radiation, catalytic processes, many things were discussed, and papers published there. But actually, there is. It's difficult to convince the atmospheric chemists is that the process would be efficient to destroy methane, and inefficient to other active species like CO, for instance, because the point is that the models, chemical models as they are at this moment, they do explain very nicely all other well, components which are measured.
Yeah.
Well, CO is one example, like a molecule which is quite stable, and well, it's similar to methane. It's stable and chemically active. It's models even explain ozone, but ozone is different case, because ozone is very much variable, and it's very much dependent on UV irradiation. So this variability is something makes it some very different from methane. But CO is a good example, which is very well explained. And well, having some exotic process would necessarily alter also other reactions in the atmosphere.
Yeah, I think that's right. Yeah, thank you.
All right, then if there are no more questions, then let us thank the speaker. Oleg, thanks so much for this talk.
Thank you.
And
Yeah,
we look forward to.
I'm very grateful. Thank you.
Yeah, we look forward to more results to know for sure whether it is fact or fiction.
Yeah. You see, there's I was obliged to update myself these days because there is a fully well, a few days ago this paper of Webster has appeared. We didn't know. Well, we were discussing that some time ago, but it appeared only now and in the form which well, I had to present it to you. Many new things happen.
Yeah, thank you.
All right, thanks so much. See you all next week. Bye-bye.
Bye-bye. Thank you.
Bye. Bye.
Thank you.